Welcome to my talk. My name is Hans Yu and I'm a PhD student at the University of Cambridge, and today I'm going to present work done in collaboration with my supervisor Matthew Juniper. This is a very long title. A shorter version which represents the gist of the talk would probably be Machine Learning meets Physical Modeling in Thermoacoustics. So the experimental system we're looking at is the probably well-known vertical Rijke tube. We have an electric heater on the inside, and we can operate it at different voltages, and in our case between 0 watts and 340 watts of electric power. The system experiences a subcritical bifurcation at around 200 watts. Below 200 watts it's stable, and above 200 watts it's thermoacoustically unstable. So it's a vertical Rijke tube, meaning the flow inside is buoyancy driven, and we infer the base flow indirectly using temperature probes, which is possible because it's a buoyancy driven flow. I'm not going to focus on the base flow model here, but just to show you some figures, these are the measurements of the temperature probes at the outlet of the Rijke tube A, and at different vertical positions at the wall inside the Rijke tube B to D. So the dots are the experimental measurements, and the line represents our model predictions, and you can see that we are able to model the base flow inside the Rijke tube fairly well. So the focus of this talk is going to be the modeling of the growth rates and frequencies, which are shown here left and right. A good question at this point would be, for example, to ask, why bother with sophisticated models and machine learning? Because essentially all these points are on two straight lines. And my answer to that question would be that in engineering we are focusing on the design of systems, meaning sure, we can draw lines, but if we want to mitigate these thermoacoustic instabilities, we can't just tell the system, for example, to shut up and be stable. What we have to do is we have to adjust the parameters of the systems, which can be, for example, the geometry, the boundary condition, the attachment of Helmholtz resonators. And therefore it's important to get a physical understanding of the system, either using models or machine learning, or in our case both. So we are trying to combine now physical models with machine learning, and if I think of a physical model, it's generative in nature, meaning we have three tiers, or three layers. We have the governing equations, the model, which represents essentially the physics. We have parameters, which characterize the system we are looking at, for example, the geometry, the exact acoustic boundary conditions, ambient conditions, etc. And we have the state, which characterize the operating conditions where the state is at that moment. So the inverse problem now would be to ask, given measurements and observations of the state, possibly partial, how can I infer what the state, the parameters, and the models are? So on the right hand side you see one way, perhaps the most primitive way of statistical learning, machine learning, which is often also shown in textbooks and discussed. It's parametric regression, in the easiest case linear regression. So the idea is that we have experiments, multiple experiments at different operating conditions, and states which we can observe at each experiment. In parametric regression we now assume that there's one set of parameters which explains all the states in all the experiments. This is a so-called overconstrained problem. It's overconstrained because we have possibly thousands or millions of measurements but only a few parameters, and this is ideal in the case where we assume that we have a perfect model and errors in the observations which we're trying to mitigate. Well, then there's the opposite scenario. Let's assume that every measurement is precise, but that our models are not perfect, meaning we need a slightly different set of parameters for each experiment. So this is a so-called under-constrained problem. It's under-constrained because, for example, our state is now characterized by a complex eigenvalue which has two numbers in it, and the parameters we have 4, 5, 10, 38 parameters which are 38 values. So it's not always possible to have a unique solution for each state, and therefore we need to do something which is called regularization. For those familiar with, for example, deep learning or the famous deep learning textbook, machine learning is essentially 50% regularization in my fair opinion. So this brings me now to our to the hierarchical framework we use. I'm not going to present the technical details here. It's good to keep in mind that for the first transition, for the first part of the inverse problem, where we go from the observations of the state to the parameters, we use Laplace approximations, or you can think of it as essentially nonlinear least squares. And then in order to regularize the parameters, we use Gaussian processes. And again, not so much technical detail, but think of the Gaussian processes as springs. In the parametric regression case, where we assume one constant set of parameters for all operating conditions, we essentially assume that we have infinitely stiff springs between the parameters, meaning they cannot move between operating conditions. In the unregularized problem, we essentially assume that we have very, very loose springs, virtually no springs. And the case of statistical learning now means that we're trying to find the springs which have the maximal stiffness, which still allows the parameters to move in a way that we can accurately predict the states. Just one more technical detail. We are using a so-called expectation maximization algorithm, because maybe you've already identified the kind of bootstrapping issue we have. If I don't know the Gaussian process, how do I regularize the parameter estimation? But if I don't know what parameters I'm estimating, how can I actually set the so-called spring strength of my Gaussian process? Without going into technical detail, we are using expectation maximization, which is an iterative process where we take one, infer the other, and go vice versa, back and forth. To demonstrate this kind of framework, I'm now introducing a first model which we're going to use for now. It's a phenomenological model, a so-called mass spring damper model, where you see the governing equation in green. And we're going to equip it with a delay term, which is quite common in thermoacoustics. Just a few words about the model coefficients like B and omega. Omega, the natural frequency, we take into account that it will depend on the speed of sound, which in turn will depend on the temperature of the base flow. And for example, we introduce a parameter called k omega, which is an end correction for the acoustic boundary conditions. The interaction index n is proportional to the heat flux, which is a first order approximation. To the electric heat. Tau is proportional to Leithold's law using a proportionality constant k tau. And in B we lump all the damping mechanisms, or possibly thermoacoustically promoting mechanisms. So we begin with parametric regression, and as you remember, parametric regression is usually over-constrained. So in theory, a subset of the observations should be enough to infer the correct parameters, assuming that the models are perfect or virtually perfect. So here we're focusing on the thermoacoustically unstable regime above 200 watts, as you can see on the x-axis. And parametric regression would lead us to the conclusion that our model is actually quite good. And we even get very decent uncertainty bars, for example, in the growth rates. If we now use this set of parameters and extend it to lower powers, to the thermoacoustically stable regime, we can actually see that our model is not as perfect as we thought in the first place, meaning that we cannot assume that parameters are constant for our very simple model. So now I'm going to show you nonparametric regression to the rescue. First again, what I was explaining earlier, expectation maximization. Iteratively, we have to learn what the parameter landscape actually looks like. So unlike the state space, where we have partial observations, where we have a fair idea of what the state looks like, in the beginning we have no idea. We have a very vague idea only what the parameters are, and using this kind of expectation maximization, bootstrapping method, it takes some iterations to improve the predictions we have, as you can see, from 1 loop to 3 loops of message passing. The next thing we can do is, and which is one of the strong points of our framework, is that we can, for example, include physical intuition that we have. And physical intuition can, for example, be that we use the information we get from 0 power. If I go back a few slides to show you our model equations, so we have 4 model coefficients, but the measurements of growth rates and frequencies are only 2 numbers. But in the special case of 0 power, n goes to 0, and we only have 2 unknowns, b and omega, and we can directly compute this. And this is, for example, knowledge we can leverage. So if I go back to the slide again, by introducing, for example, knowledge we gain about b, the damping coefficient, we can already significantly improve until we are virtually predictive actually over the whole range. To illustrate what we just did, I'm going to look at the model coefficient b now instead of the state, the growth rates and the frequencies. And on the left-hand side, we can see what no information essentially looks like. So the Gaussian process tries to be as stiff as possible, and so it tries to maintain this kind of constancy, this kind of constant values for as much of the operating regime as possible. It realizes that for the lower powers, it's not possible to stay constant anymore. It moves up, it slightly overshoots, and then it reaches this kind of value at around 7. If we now communicate to the Gaussian process ahead of time, saying you don't have to stay constant the whole time, because we know at 0 you're going to have a value of approximately 8 or 9 anyways, the Gaussian process, it looks slightly different. It starts to slightly deviate earlier for the model coefficient b, and has this kind of small change which has a big impact if we go back one slide earlier. So this is how we can make a qualitative model quantitatively predictive and accurate. Now I'm going to talk about the second issue, model selection. And for that I would like to first introduce actually a second model. So the second model we're looking at is a so-called network model. And unlike the phenomenological mass spring damper model now, this one is based on first principles. So assume we divide the Rijke tube into segments where we have forward and backward traveling waves, and they're coupled by jump and boundary conditions. And you can already see, due to the length of my explanation, that this model is more physically sophisticated. So we establish a similar bench line as earlier by looking at parametric regression first, and we can see already that that the model is qualitatively quite good. We can see starting at around and below power levels of 100 watts that the growth rates are not quite perfect, not even qualitatively, and that the frequencies, there are slight deviations. Skipping a few steps, which we did for the mass spring damper model. So this is after using the expectation maximization algorithm, which slightly improves the growth rate and very clearly, for example, improves the frequency predictions. And now introducing again physical information. For example, we can, again similar to the mass spring damper model with the damping coefficient, we can very accurately measure the reflection coefficients of our of our pipe at 0 power. And if we now introduce this information among others, we get a very, very predictive model. One of the most noteworthy things I always find is that we can even pick up a certain waviness below the power of 100 watts, which is actually very difficult to see with the naked eye. So now we have a second model now, and comparing it to the first model, under usual circumstances, the comparison, it's an apple and orange comparison, depending on what the preferences are, what the computational resources are. And now we're going to talk about how we can statistically measure which is the better model or the worse. Traditionally, how we would do this in parametric regression, from a probabilistic point of view, is this kind of maximum likelihood function. And I would like to direct your attention to the content, to the argument of the exponential function, because this is essentially the least squares you might be more familiar with. So y is the observation of the complex growth rate and frequency. S is what we would model based on our what we would predict based on our model and our parameter theta. And the matrix we use to weigh it with is this sigma observation, which is the measurement error. On the other hand, in our evidence framework with nonparametric regression, we use a different metric, which is the so-called marginal likelihood, or the evidence. And again, I would now focus your attention, or I would direct your attention on that we're now using a slightly different metric. It's derived using Bayes' rule, which I'm not going to discuss any further, but it's statistically rigorous. And interestingly enough, it not only considers that there are errors in the measurements, but it also takes into account the covariance function of the Gaussian process, sigma jp, and the derivatives of the eigenvalues with respect to the parameters, meaning it takes into account not just the fit of the observations versus the states we predict, but also the complexity that our model of the parameters has, as well as how sensitively actually the states react to small changes in the parameters, which is often a big issue in thermoacoustics. So this may be slightly anticlimactic, but this should actually be the climax now of this presentation, this table of values. So this tracks the progress we made on our models, the mass spring damper model, MSD, and the network models, following chronologically the improvements we made, starting from without using any expectation maximization to actually including physical information. And we can see how both the maximum likelihood and the evidence improves. Improvement means that we have less negative values or actually positive values in the ideal case. And we can see, for example, one interesting thing. We can now make the apple and orange comparison. We can tell that the network model is better than the mass spring damper model, which is not obvious. In the evidence, we can see that our improvements are usually a bit more conservative. And this is related, if we look at the first three values for the mass spring damper, this is related to the fact that by adding physical information, we, for example, increase the complexity of the model. If we compare the network model to the mass spring damper models in general, we can see that the maximum likelihood makes a bigger jump than the evidence. And this is, for example, related to the fact that the network model is more sensitive to its parameters, especially the reflection coefficient. For an acoustically open-end, it's always close to -1, but small changes can make a very big difference, meaning that the network model is better, but not that much better if we think about this, because the model parameters are so sensitive, while the damping coefficient B, which we used in the mass spring damper model, although it lumps a lot of things together, it's fairly robust. Well, this already leads me to the conclusions of this talk. As I said, this talk was about essentially machine learning meets physical modeling, reduced order modeling, and thermoacoustics. And one thing I think we are always looking for is we are trying to find simple models which inform us how we have to change the system to mitigate thermoacoustic instabilities, but it mustn't be too simple, otherwise we have no accurate predictions. The key features of our physics-informed statistical learning framework is, firstly, it's generative, so we retain the way we model traditionally using states, parameters, and model equations. Additionally, we use Bayes' rule, which makes our model probabilistic. So in addition to improved point estimations, we attach all our estimates with uncertainties. And lastly, and this may, for some people, maybe be just a practical concern, but I think it's quite important, is that our framework, and the emphasis is on framework, is quite flexible. So for the inference of the parameters from the states, we use Laplace approximation. Other people would use Markov chain Monte Carlo, for which there are oftentimes off-the-shelf solutions. On the other hand, if one has a very clear understanding of the model's first and second derivatives at one's disposal, Laplace approximation is very efficient. On the machine learning side, this also gives us a certain flexibility. We can use Gaussian processes on neural networks or other kinds of techniques, and it would be interesting in the future to benchmark different techniques or different components and elements in our statistical learning framework. Well, thank you very much for your attention. This concludes my talk, and I'm looking forward to meet everyone at the panel session on Sunday. Cheers.